I'm Bill Bain from Scaleout Software, and so I was trying to think of the best way to marry our talks, if you will, the topics, and I think the best way to think about what I'm going to talk about is that what underlies analyzing all this data and trying to understand the correlations and whatever patterns we need to learn is to have computation that will scale with the computing resources we have so that we can actually tackle all this data and get useful results in a reasonable amount of time. So this talk is about scaling computation. So I'm going to talk about the need for scaling computation and how this technology that we've developed at other companies as well, we call it distributed data grid. You might have heard the term in-memory data grid or distributed cache. How this technology has evolved to tackle the problem of scaling computation. And also, I want to talk about how this technology compares to NoSQL stores. I was actually expecting Rick to talk more about the various NoSQL technologies out there, and I wanted to separate what we do from that. But I'll just touch on that maybe a little more than I would otherwise, and tell you a little bit about how we build our technology, how we deploy it in the cloud, and how we use it to do analysis in parallel of data to get results very quickly on important questions that need to be asked of the data. So, okay, here we go. So, start small. We have a classic computer. I want to sort of put everybody in the same grounding. I'm basically going to tell you what I learned over the last 30 years in a nutshell about scaling computation. So, back in the 70s, when people were first trying to scale computing out of the box, the easiest thing to do is just to build a bigger box and put more processors in it. And today they're cores, but in the old days they were just processors, multi-proc boxes. And the reason why that's useful is because it makes designing applications very straightforward and simple. And because the way you design applications for a single server, more or less you could design with some techniques for a scaled up system. The problem is that there's a limit to the amount of scalability you can achieve that way. So people learned in the, I would say the early 80s, really that the way to go is what's called now Scaleout. And that's why we call our company Scaleout Software. But this term was actually coined by a gentleman at Microsoft in about the year 2000 and was widely used. The beauty of scaling out is that you can get really excellent scalability. You can scale almost in an unlimited manner. There are limitations usually end up being power or interconnect performance, but the limitations are much wider than for scale up. In fact, there was a company in Portland, Oregon named Floating Point Systems that proposed a computer that would have some very large number of nodes, and then they realized one day that they couldn't actually physically build the building. They couldn't get the power in the building, and they couldn't make the floor strong enough. So the limitation had nothing to do with any of the computer science. But the real problem that's always haunted scaled out computing from the earliest days, it's very hard to program these kinds of systems. And the reason is because the way you write programs for a single system will not map to a large number of computers, because you have to write the code to run on all the computers and to access data in separate memories and to tie together the various storage systems of the different computers. So it's a very hard problem. And so one of the ways it can be solved is to start attacking the problem at the storage level and the memory layer. And so one of the reasons that I'm going to present this slide is to really sort of set the scene for NoSQL stores and distributed data grids. So you can see this talk is a little different than the earlier one. I hope it's what Don wanted. Where's Don? Yeah. So I hope it's in the right level. If not, just wave at me and I'll shorten it. Okay. So one of the problems that the NoSQL technologies have sought to attack is how do you scale persistent storage. Now, Rick has enlightened me that he views NoSQL as encompassing memory as well. For the purposes of this talk, NoSQL stores, I'm talking about persistent stores, stores that are storing data over a long period of time on a disk, on some kind of non-volatile medium. And so, one of the challenges is how do you get away from the constraints that the relational database technology, SQL, ACID compliance, these are terms that are used in that field, impose. And people have found, I think that's why that term NoSQL emerged. Rick could tell us, maybe afterwards we could talk more about the emergence of that term. But really it's to say, oh gee, if we can relax that and maybe get away from ACID. In fact, they coined a new term called BASE, B-A-S-E, which is a different acronym. Then that all of a sudden now you can build these scalable storage systems. And in fact, one of the real accomplishments of the NoSQL technologies is to actually design targeted stores for various types of data, columns or documents or graphs. Other things that, like, for example, document hierarchies to match web documents and blogs about web documents or whatever. So you can actually build special purpose stores for various purposes. And also both for persistent storage, and we'll learn for memory storage, you want to have high availability. So now you have this challenge because you can lose servers. And when you lose individual servers, you could lose some of the data, you could lose some of the computational ability. So you have to attack the problem of failures. And I can just tell you, in our experience in the last, 8 years building distributed data grids, is that availability is the problem that's the hardest to solve. I was warned about that, and I didn't believe it, and now I've learned that is where most of our, I'd say 90% of our support requests are in the area of availability issues. So just out of interest. So NoSQL data stores really are attacking the problem of how do you bring these stores into a unified whole to make them usable in a scaled out environment. Now the problem we've attacked is how do you take memory that's spread across these systems and unify that. The big problem that you have here is that you want to share, you want to allow applications that are running on these computers to share data across the memories and not have to explicitly do it. When people first built these scaled out systems, and they call them parallel supercomputers, then they realized that they had this problem and they solved it with what they call message passing. So a program would send a message to a program on another system and back and forth, and it turns out it's almost impossible to make that work reliably. Some of the very big simulation models we see that are deployed on these kinds of systems are implemented with message passing, but it takes months and sometimes years to develop them. And they tend to be fragile, so you can't really modify them. So that's really not very helpful. What people did when web server farms emerged back when I started this company right before that, we saw the beginnings of web server farms in 1997. And what people did to solve that problem is they just sidestepped it. And they would, instead of storing data that needed to be shared in memory, they just go ahead and push it to a database server. And what they learned is that database servers can become overloaded by doing that. And so it became obvious that you need to do something that allows you to have memory that scales and yet is very easy to use. And the answer to that is, of course, the distributed data grid, or some people call, some of our competitors use the term in-memory data grid. There is no standardized term, unfortunately. We need a standard term for this technology. Now, what we're seeing evolving right now is there's really some confluence of these technologies, and Rick can actually, he's more expert on this than I am, and he can tell us about that, but our focus has been on making shared memory, memory that spans multiple servers, be shareable across these servers, and to, by doing so, scale computation. The persistent NoSQL stores also use memory for caching and other purposes to implement MapReduce, but their focus is really on persistent storage primarily, and then computation of that storage secondarily would be my view. Our focus is primarily on scaling computation, and that's also the focus of this talk. So let's just talk about what a distributed data grid is. I said why we need it and how it can be valuable. Well, what is it exactly? Well, one way to think about it is it's this missing level in the storage hierarchy. If you think about it, and this gets a little technical, there's various, people talk about layers in the storage hierarchy, from disks to memory for an application to processor caches and so forth. Well, there's always been this missing level, which would be memory, but memory that's not within an application's process, but it's what's called out-of-process memory. And the distributed data grid actually fits in that level. So it's out-of-process storage. It's a little farther away from the processor, but it's much closer than a disk. So in other words, the access time is much faster than to store that same data in a disk. And where you see this applied is when you have fast-changing data. So if you're on a website, you're on Amazon, and you put something in a shopping cart, you want this to happen quickly. And so if you can store the shopping cart in memory, you're going to get much faster response time than if you have to push it to disk. Now, it's also a scalable tier, so it's not just a new layer in the vertical hierarchy, but it's a new horizontal storage tier, and it allows us to then scale out computation because of the fact that it provides the shareability amongst the servers. So this technology, called the distributed data grid, one of its main purposes in life is to create a mechanism by which applications can share data. And what I mean by that is that if an application puts what we call an object, a piece of logically related data in the grid, any other processor any other server can retrieve that data. And it doesn't have to worry about where the data is stored or how the data is spread across the servers. It's just automatically available just by having a key to that data. It's what's called a key value stored in memory. So distributed data grids provide this data sharing, and they also at the same time provide a scalable storage resource, because as you add servers, you're adding memory for storing data, and you also are adding speed, performance. So as you add servers, then the whole distributed data grid will go faster and faster. And they're designed to be highly available. This, I just want to watch our time here.
Can you take a question?
Yeah, sure.
Yeah, quick one. Just wondering, I know that you were focused on heavy data, big data problems, but do hypervisors play in this at all? Or is that going to detract too much from performance?
Yeah, hypervisors play because they tend to create performance issues for any of these kinds of, this is a middleware technology, and they create issues for it because they create a platform that's really unreliable, unpredictable. So in other words, the amount of actual memory that the grid has, if you think about this, a certain amount of memory is dedicated on each server to the grid. Well, the operating system thinks that that server has that physical memory, but in fact the hypervisor may take it away and not even tell Linux or Windows, and so the end result is that it does not behave the way the application expects it to behave. So
is this becoming a bigger challenge
in the cloud, right? Exactly.
But
yes.
Does this, modality create a bigger issue in clouds and federation and whatnot, where now it looks like a big metal type of model?
Okay, so I'm assuming you can hear the question. Okay, so it's both a it's a blessing and a curse. It's a blessing because the cloud creates a huge computing environment. It gives us the ability to deploy on hundreds of servers applications that otherwise we couldn't afford to buy the servers to use. So now we have the ability to use those servers, but unfortunately they're virtual servers. So, just as I think you were saying, Rick, earlier about making sure you're getting the, I forget the term you used, making sure you're getting, there's no leaks, that you're getting all the CPU resources that you think you're getting.
Don't water down the sewer.
Yeah, that's it. That's the challenge. And so actually in our newest version, we've specifically targeted that problem, and our software is now designed to better handle the unpredictable nature of virtual servers. But it's a reality, it's a fact of life. And if you're going to run in the cloud and have access to hundreds of servers, you have to accept the fact that hypervisors may do things which impede performance. So you make the software as resilient to that as possible. Okay, so one of the other things that's really cool about this technology is that it adds another layer besides the two I spoke about. It adds a layer inside of the process itself to cache recently accessed data. And what that means is that data that's in the grid is much more readily accessible than in a database server, but when you have a client-side cache, then it can accelerate access even more. And that's a really unique capability of a distributed data grid that adds a lot of power because it's reducing access time. And in fact, here's an example. If you compare accessing data in the grid to accessing it from a database server, you get like a 6x improvement when you have a 20-to-1 read-to-update ratio. The client-side cache is only good for repeated reads. And this is a really strong benefit, and it shows you the power of using an in-memory grid with an integrated and coherent client-side cache. So that's just an example. So this is just to end the first section of this talk of what is a distributed data grid. This sort of captures the key values that you get from it. You get very fast access time, and you get this scalability, both in capacity and throughput. And the scalability is best seen here. This is a graph that shows you the latency, the access time, the time it takes to retrieve data or put data in the grid versus the throughput that the grid is providing. And you can see that, a distributed data grid, which is this lower line here, I talked to you about the access time a minute ago. You can see that relative to a database server, it's much faster because of the client-side cache. But the other aspect that's really good is that there are no real limits to throughput gain as long as you have enough interconnect speed and power and so forth. So, whereas you hit a wall with any fixed resource like a relational database server, then you don't hit a wall with a scalable resource, a scaled out resource like a grid. The same graph could be applied to NoSQL persistent store. So in fact, that is one of the key motivators. It's you want to overcome this wall that a single relational database server provides, and you do so by creating a scalable storage medium. Now, relational database servers are important and will be with us for a long time. In preparing for this talk, I was reading this article about NoSQL stores, and And basically, people are trying to yank out relational database servers because they're extremely powerful and valuable for a company's data and searching it and so forth with the SQL. But the idea with NoSQL stores and distributed data grids is to limit their use for the target uses that they're most valuable for, and then to migrate to other stores when you don't need the semantics and the ACID semantics that are provided by relational database servers. So to sort of limit their use and not eliminate them in the near term. Over the long term, we may find ways to eliminate them, but maybe not, who knows. All right, so this is one example of how a grid would be used. It'd be a web server farm. So this is a web server farm and an application server farm. I used to work at Microsoft, and this is a picture I took right out of Microsoft. That's the way they would draw these server farms. So they would have, application server farm is doing business logic, like a BizTalk server or a commerce server, and then up here would be web server farm. And then you'd have the database server, relational database server in the middle. And when I joined Microsoft, people were storing all of the fast-changing data, like shopping cart, session state, in the database server, and observing that it was quickly becoming a bottleneck. So an in-memory data grid will eliminate that problem by storing data, as I said, in memory that spans all the servers, both in the web server farm or application server farm. And by doing that, you offload the database server, which tends to be very expensive, and you also get much better performance, and it scales as your server farm scales. So it's pretty much all wins. Cost-effective and highly scalable. So another use which is emerging, and this is a targeted use of our product coming up in the next couple of years. We'll be releasing a product to support it very shortly. This is not a vendor pitch, but just telling you, is to use the same technology in the cloud. I'll just say, other commercial vendors have been in the cloud for some time. Gigaspace is an example. I know Amazon has deployed Memcache in the cloud, so it's not new to use this technology in the cloud. We're targeting it for some reasons I'll talk about later, but what you see here is these are the virtual servers that we were talking about a minute ago, and it's an application that runs across several virtual servers, so it's trying to enjoy the elasticity that the cloud gives you, and that's the real benefit of the cloud for scalability. There are other benefits, but one benefit is now we can deploy a scalable application and pay on demand, pay only when it runs and not pay all the time. That's a huge win because 10 years ago, if you wanted to have scalability, you had to buy a cluster, and only departments and larger could afford clusters, and very few people could deploy supercomputers except the national labs and so forth. So what the problem is, you're faced with that same problem. How are they going to share data in a scalable way? And that's where the distributed data grid comes in, because it also runs in another set of virtual servers, and it allows the application to very, very easily push data into the grid and keep it, and not have to push it all the way to the cloud-based store, which can be relatively slow, and share data very, very quickly amongst those servers. So that's a second usage, and that's how in the cloud we expect people to actually deploy distributed data grids. Now, and I'll come back to the cloud in just a minute. And, I think I might just skip this. This is talking about what it is, what scalability means, and I'll just be very brief on it. We're running a little. We want to be stopping this by 7:15, right? So, yes. All right. So scalability means that as you add workload and add servers to handle that workload, the throughput of the system is increasing linearly. If you don't have a scalable system, it behaves like this. It hits some bottleneck or a wall, as I showed you before. So a scalable system will linearly increase its output as you add workload and servers to handle it. And distributed data grids use a variety of techniques to achieve that. They distribute the data across the servers, they provide high availability, they synchronize accesses, and they load balance the data, and they detect server failures and handle it. And I won't talk any more about that tonight, so the talk doesn't run too long. Let me just say that you can apply this kind of technology to a variety of applications that need to be scaled out. Many applications I'm sure you understand in financial services, many in e-commerce and back office applications, business intelligence, and we have customers in many of these areas. In addition, there are applications which we don't really attack, which are very a good fit for distributed data grids, namely game servers or command and control, managing logistics. We were talking to somebody yesterday who wants to deploy this kind of technology for the smart grid. So to capture real-time data about nodes on the grid that have solar cells, and to compute where to push the energy so it's most efficiently used at any given time. So there are any number of applications that would fit this usage because they are scaled out. There's a large amount of data, and that data has to be analyzed quickly. In cloud computing, I think we talked about this. It has elastic resources, but one of the things I didn't mention is the interconnects are relatively slow in addition to being virtual servers. And so distributed data grids add a lot of value because they can kind of mask the relatively slow interconnect you find in the cloud. And the way they do so is they keep data in memory instead of trying to ship all that data out to a secondary store. And also, you can compute on data in place and not have to move it around between virtual servers in order to do the analysis of that data. So here are two examples of how we expect customers to use distributed data grids in the cloud. One example would be a web farm that, say, runs on premise. That means at some customer site. I use the example, flowers.com, right? So, and then it's Mother's Day, and so all of a sudden they know their web traffic is going to grow by 10x. So what do? They cloud burst is the term that we're starting to see. So they spin up some web servers in the cloud on virtual servers, and now they have the problem. They're going to turn on the load balancer and tell it, okay, I want you to send some incoming requests over to the cloud, so we'll balance between on-site and the cloud. And one of the things the grid can do is it can automatically migrate the shopping carts into the cloud for you, so that the customer doesn't have to find some way to take this data, put it in a database, ship it over to a database here, and then load it back in here when the web load balancer directs a request here. So just based on the customer's login cookie, this virtual server could say, I need a shopping cart. The grid will detect that the shopping cart is not located here, it's located on premise. It will move it through a wide area network to the grid, to the cloud, and then make it available as if it had been there all along. And this is a capability that a grid can give you to offload the need to move data through secondary storage to get it from one site to another. Another scenario that we've seen, oops, there's the grid. That would be, if you will, a virtual distributed grid. Another usage model, which we've had customers request, is to not only allow you to mirror data between sites for disaster recovery, but have the ability to retrieve data all over the world as if it were just located locally. And again, it's moving data over a wide area network, memory to memory, so that it doesn't have to be pushed by the customer through another means. This particular customer was using web services requests to manually retrieve data from the US, take it to Hong Kong, dump it into a grid there. And there's a lot of what we call plumbing code to do that, and that's just basically eliminated by the use of an in-memory, just globally distributed data grid. Now, I'm going to switch topics to the final topic tonight, which is data analysis. And this sort of builds on what Rick was talking about, the need to analyze large amounts of data and to find the patterns and trends. And that's something that really, that scalable computing through scaled out implementations can deliver. And the term that was coined and used as a tagline for Microsoft's cluster server, fast time to insight. So what it gives you is fast time to insight. And here's many applications. Many have been around for decades. Some are relatively new. This is a climate model, which I saw last year at the Supercomputing Conference. I put the link in here. If you get this talk, you definitely should go follow this link, even if you don't care about this talk. This shows you their climate model. This is the National Center for Atmospheric Research. They did a climate model modeling temperature going back. They went back 100 years. I think it started in like 1850 or something, 1840, and they go to 2100. And they show you, this I think is at 2100. I'm not sure, but basically it goes from nice pretty green-blue colors to that by 2100, and it'll scare the heck out of you. So if models are, they say that they're like 10x away from having the granularity in the model to really understand enough detail and say, and for the scientists to actually say, it's right. So that's one of the problems, but they're pretty close now, and this model is getting very close to where they'll stand behind it and say, we really believe this is going to happen. But in any case, it's an example of parallel computing because you're taking all the data for temperature, winds, and and effects of the Earth, evaporation, and you're breaking up the Earth's surface into little segments here, and then they talk to each other, they compute and communicate and compute and communicate. So it's a classic example of parallel computing. So this is one of the things I want to do is, I think this term MapReduce is so popular. And I wanted to give it a context and let you know, it's really been around for a long, long time. It just has had other names. And as far back as I looked, and it goes farther than this, but basically a guy named Mike Flynn coined this term, SIMD, Single Instruction Multiple Data, way back, I think in the 70s. And this guy named Danny Hillis, who you may have heard of, because Richard Feynman worked in his company for a year or two. But Danny Hillis, I think, went on to Disney. But he invented this machine called a connection machine, and it was a parallel computer, but it used special purpose hardware. But, today, this machine, if it had today's technology, solving the same kinds of problems that we solve today with big data. Now, what happened is in the 90s, this was in 1984, in the 1990s, companies like Intel, IBM, and I worked for Intel Supercomputing at that time, I worked on this computer, built general purpose parallel supercomputers. So they look like that picture you saw in the beginning of scaled out, but the software was very rudimentary because it relied on this message passing. We didn't have distributed data grids and NoSQL stores. So Intel cobbled together a parallel file system, but today's NoSQL store would really be much more powerful. But we used the term back then, domain decomposition, or single program multiple data. So this term for parallel data analysis, the point of this is that term, which we now call MapReduce, has been around in with other names for many years. Now, cluster computing became popular in the 90s and 2000, and that's when we saw Google start to actually make popular the term MapReduce, and I'll talk about a specific MapReduce example in a minute. And this has been implemented by both distributed data grids and NoSQL stores, some commercial, some open source, and that's just an example of a cluster computer. So you can see how this technology has been evolving and moving towards more general purpose hardware, and now the next step is, of course, deploying it in the cloud on virtual servers. So we've come a long way since 1980 with doing parallel data analysis. So I'm going to give you a quick example of it, quickly running out of time. What you really want to do is take a set of data, and you want to examine each data item and try to understand something about it. So you run a piece of code, or what's called a method called eval here. So you would run that in parallel across a bunch of data. That's the lever that parallel computing gives you, that scaled out computing gives you. The ability to do all of that in parallel if you have enough computers. And then you want to combine the results. That's what in MapReduce is called the map part. You map out your evaluation to all the data and select the data of interest and evaluate it. And then you want to combine the results. So a full combination of results would look like this. So with a binary tree, you combine it down to one result. And now you understand a lot about what you were examining. But I'll give you a specific example in a minute. So here it is. So say you're going to backtest a trading strategy at the stock exchange. So we did an example with Lab 49 you may have heard of in order to just see, okay, how would you use our MapReduce and what kind of performance would you get out of it? And we said, what would be a really good example? And backtesting, a stock trading strategy is a perfect example because you would have many years of stock histories, as many as you have ticker symbols you want to examine, and a lot of data for each ticker symbol, say 10 years of profit and loss for every day or for even times during the day. And then what you want to do is in parallel, you want to evaluate this trading strategy or a set of trading strategies for a given stock ticker symbol. When you finish doing all of that, you can imagine that's a lot of computation. It happens in parallel. Then you want to merge all the results so you can come up with a result. Yes, this stock trading strategy beat my previous one, or no, it's a bad idea. So this is just a simple example. So graphically, these are the stock ticker symbols in ugly turquoise. And so what you can do is in parallel, you would examine them, and then you merge the results in an intelligent and powerful way. Now, if this data can be held in memory, you're going to get really high performance because the data, in a distributed data grid, the data will actually stay in place. And the key thing to observe about an in-memory distributed data grid is we can do the evaluation in place on the grid servers and not have to migrate data from one server to another. And you'll see the impact of that in just a second. Now, if you have to store the data in a file system or a database, then every time you do this computation, it has to move in memory, and then the evaluation is done, and that really slows it down. We did a test. It was a slightly different test, but it was actually more benign than moving data from a file system. We were just doing random access to objects to simulate I/O. So instead of having to pull the data from the file system, we were just pulling it from a remote node across the network. Equivalent amount of I/O. In fact, less, because if it happened to be local, it wouldn't move at all. Whereas with file I/O, all the data moves. But you can see that what we found is the scalability of a system that's moving data across the network is much lower than one that keeps the data in place. We were doing some studies with Hadoop, which is a technique for doing MapReduce for very large data sets, but it's based in a file system. Of course, you can't hold these large data sets, and many of the ones that Rick was talking about, you can't hold them in memory. So that's the challenge. So if you have to put them in the file system, you'll suffer some scalability loss, but you will get the ability to handle large data sets. We ran a test, and what we found is that if you can hold the memory in the grid, we could do this particular test with 4096. We were doing it, we just measured this the other day with Java. This was all done in C#. And we found it ran in between about 2.5 seconds to do this particular exact test. And on Hadoop, we were measuring 42 seconds. And that's all file I/O. It's the same computation precisely. It's all file I/O. So if you can hold the data in memory, you get much better performance. This sort of gives you a sort of a table of when you would use file-based MapReduce versus a distributed data grid. And I think it really turns on the size of the data set. And what we found is many financial data sets will fit in memory comfortably. But many useful data sets, census data, climate data, that's going to take a file system to hold it. The other thing is that it turns on is the best use in terms of quick turn. So if you're a quant and you want to just test a strategy and you want a result now, or maybe even you want to automate that and in real time go test a strategy and spin it up, not as a batch job, but just as a method invocation, you can do that easily with an in-memory grid. But if you want to do a very complex analysis, of a large problem, look for patterns that might be elusive, and you're willing to spend the time to do the tuning required to make it really work well, then a file-based MapReduce today would offer you a better environment. So the challenge that I see, the next step, and this is my second to last slide here, is how do you get data closer to where it's being used? Because we just saw that in some cases you need to use file-based data, right? It's a large data set. And so the data is in backing store. Well, maybe we can do better. Maybe we can actually prefetch the data or avoid unnecessary writes to the file system and use the grid in a very intelligent way so we can get the benefit of having the grid while having the benefit of having the large file-based store to hold the data originally. And that's an area that we're working on for future products. And there are other ways we can optimize performance, but we could talk about those in another discussion. And so in summary, really scaling out is the way, it's the technique people have discovered to really get very high scalability so we can tackle these big data problems and to actually be good stewards of the data age, if I might say that. And distributed data grids are one of the tools in our toolkit that allow us to do that by holding data in memory so that it's shareable, highly available, and can be accessed very quickly, and can integrate support for this parallel data analysis. Clouds are going to be the deployment model of choice for big data in the future because of their huge elasticity and ability to hold large data sets. And I think the big challenge that we see coming is how do we really take performance to the next level so we get really fast analysis over very large amounts of data. So thanks very much. I appreciate that.